Hello everyone, welcome to Sri Chaitanya Academy. So I also welcome you to this fourth session of the chemistry transition course, where in the last class we studied about the mole concept and how you can arrive at moles from number of particles or from volume of gas at STP or mass, and then in the next class of that class we applied them to solving questions. In today's class we will move forward to chemical equations, where we are going to talk about a particular concept called stoichiometry, which is useful to solve each and every question that we will encounter in the chemistry part, right? So now let's start this. So this particular word called stoichiometry, what is this stoichiometry word? It is the area of study pertaining to study of quantitative relationship between reactants and products. So it is a study which talks about quantitative relationship. Now quantitative means numbers, right? Like 1 gram, 2 gram, some number will be there, right? I will not say that just carbon reacting with oxygen forming carbon dioxide. I will not just say this. Not only carbon reacts with oxygen to form carbon dioxide, but also I will say maybe 1 gram of carbon reacts with, this is just hypothetical, 1 gram of oxygen to form 1 gram of carbon dioxide. So when I specify the grams, the amount of the substance, then it is stoichiometry, right? So now, the chemical equations, right? Whatever chemical equations that you are going to write in chemistry till now should follow the law of conservation of mass, right? They should be balanced with respect to number of atoms of each element involved in the reaction. So what I am trying to say here, that if you have an equation, suppose this is the arrow, the mass of everything here, right? This is, okay, this is for you which side? This is your right hand side, this is your left hand side. So for right hand side, the mass should be equal to the mass on the left hand side. Not only that, the atoms of various species, atoms also should be equal, okay? Right? When this is there, then the equation is said to be balanced, right? So the mass of everything on this side should be equal to mass on this side, and number of atoms on this side of a particular species. Suppose if you have carbon plus oxygen forming carbon dioxide, right? So so what I mean by number of atoms, I have one carbon atom here, right? And exactly here I have two O atoms. So same here also I should have two O atoms and one carbon atom, right? So one carbon here, two O here, two O here. So when you balance a chemical equation, right, should be balanced. What this balanced word means? Balanced word means that atoms of different kinds should be the same in number on both sides of the equation. So you have to just do that. So next I'm going to give you some basic logic and some stepwise way through which you can balance most of your equations, not all, but most of them. We will also learn about some other methods of balancing in the future in this transition course. But for now, let us stick to something simpler. So balancing of chemical equations by trial and error method, right? Does not work always, but will work in some case. So this is the equation example I'm going to take, and one by one, we will apply these steps to balance this equation out. The first is, the number of times an element appears on the reactant side. This is the reactant side, this is the product side, and the product side of the equation is counted, right? So now you count. So here you have how many potassiums? 1 potassium. Here you have 1 potassium. So your potassium is equals to 1 here. Hydrogen how much? 2. Here also 1 potassium. Hydrogen how much? 2 hydrogens here. So you will say that hydrogen is 2, right? Here how much hydrogens? Hydrogen is 1, right? Manganese here is 1, so this will be 1. Here also manganese is 1. Oxygen here is 4 plus 2, so you have 6 oxygens here, and here you have 4 plus 4, 8, 9. So you have 9 oxygens. And iodine, here you have 1 iodine, here you have 2 iodines, right? Now, after you find the number of each species on both sides, next you check the element which is least in number, right? And use that to balance. So the element here least in number, what I am finding is that it is potassium, because potassium is 1 here and 1 here. Here iodine is 1, here iodine is 2. So let us balance potassium first. So after you are done away with this, let us balance potassium first. So let me clear this out. Right. Now let us balance potassium. Balancing essentially means making the number same. So here potassium is 1. Here also potassium is 1. I think it is balanced. I don't have to do anything else. After potassium, which other element? Actually, I did not see this. Sulfur, you can see 1 here, 1 here, 1 here. Right? And the next element was iodine. Now, after you have balanced the first element, then you move on to the second lowest element. The second lowest element here is iodine. You can see there are 2 iodines here. So to make this 2, multiplied by 2, right? Right? This balances iodine. Now moving on to the next lowest element, that is sulfur here. Right? Here are 2 sulfur atoms here and 1 sulfur atom here. How to make it balanced? Simply, you can put 2 here. Right. After this is done, let us see manganese. Manganese is perfectly balanced. We don't have to do anything. Now what else should we balance? What else should be balanced? Now see here, potassium now is 2 here. So I will put 2 here to balance the potassium out. Right. So when I do that, right. So when I do this, what happens is now sulfur becomes 3, right? Now here you have 3 sulfurs and here you have 1 sulfur. Now to balance these 3 sulfurs, you have to put 3 here, right? One thing which I skipped was I have to completely balance potassium. Listen carefully. The first was the lowest number, I had put 2 here. Right? As I put 2 here, iodine is balanced, right? Now moving on to potassium. Potassium becomes how much? 2 here. But here it is 1. So I have to balance potassium, I have to put 2 here also. After potassium is balanced, I checked manganese. Manganese is already balanced. And then I move to sulfur. Here you have 3 sulfurs, so here I will put 3. Right? After that, see hydrogens. Right? The next lowest number is for hydrogen. Hydrogen, there are 6 hydrogens, 3 into 2, 6. Here there are 2 hydrogens, right? And I need 4 more hydrogens. So I can put here 2, I'll get 2H2. So 4 hydrogens here. Then finally, let us see whether the oxygens are balanced. Here you have 12 plus 2, you have 14 oxygens, right? Here you have 8 plus 4 plus 2. Yeah. Here also you have 14 oxygens. So it is balanced. Now, the element which appears least in number is balanced first. The other elements are balanced in increasing order of their frequency, right? In case any two or more elements have the same frequency, if the frequency is same, then metallic element is balanced first in preference to the non-metallic element, right? So in this way, you can balance any equation. Count the number of atoms on both sides. The lowest atom gets balanced first, moving on to the next higher one. And then if they have the same, then metallic gets balanced the last. Now, if you see this particular equation, or I just take one more equation. So let us take this equation. N2 plus H2 NH3, right? So in this case, how will you first have to balance this? How will you balance this? See, there are two nitrogens here, one nitrogen here, three hydrogens here, two hydrogens here. So obviously you will balance nitrogen first. As you balance nitrogen, you'll put two here, two nitrogens done. Now, hydrogens 3, 2, 3, 6 hydrogens here. Now, how to balance 6? You put 3 here. Now, this balanced chemical equation is what we call as the stoichiometry. It tells us about the stoichiometry. What does it mean? First, focus your attention on something which is this. Here, if something is not, anything is not written in front of a symbol, it means that it is 1. Okay. So this 1, this 3, and this 2. What are these called? Right? What are these called? These are called stoichiometric coefficients. Stoichiometric coefficients, right? Now, these stoichiometric coefficients have many meanings. The first meaning is that one nitrogen molecule reacts with 3 hydrogen molecules to form 2 molecules of ammonia. Not only that, it also means 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to give you 2 moles of ammonia gas, right? So the interpretation of the equation that I want all of you to remember is that, right? 1 minute. I think it all got erased. Let me write it down again. Right. So the definition I want you to remember is, here you have 1 mole of nitrogen, right? And then you have 3 moles of hydrogen reacting to form 2 moles of ammonia, right? So the number of moles of various reactants and products involved in the chemical reaction is indicated by the balanced chemical equation. Remember, this has to be a balanced chemical equation, right? Now, these chemical equations tell you some kind of relationship between the chemical substances. Now, what is that relationship? It can either be weight relationship, weight volume relationship, or volume relationship, right? So these are the relationships which it can talk about, and how does it talk about those relationships, we will see further in detail in the next parts. Now, weight relationship, how do I talk about weight relationship? So I'll take the same thing. In this equation, nitrogen's molar mass is 14. So if I say 1 mole of this reacts with 3 moles of this to form 2 moles of this, right? The molar masses of this is, if I talk about the molar mass, this is 28, this is 2, this is, nitrogen is 14, right? With 3 hydrogen, 14, 15, 16, 17. Right? So you have 17. So this is in grams per mole, right? So now, right. So now you calculate the mass, right? If I talk about the mass, 1 mole, this will be 28 grams. How will you calculate the mass? Just multiply the moles and the molar mass. 6 grams this will be 34 grams, right? So this is the mass relationship, right? This is what I mean by the mass relationship. The 28 grams of, so now if I have in a chamber, in a vessel, if I have 28 grams of nitrogen and to that I add 6 grams of hydrogen, then I'm bound to get 34 grams of ammonia. That is what I mean to say, and this is called your mass or weight relationship. Let us have a question on that. Calculate the weight of zinc required for the liberation of 10 grams of hydrogen gas on reaction with H2SO4. So now you have zinc, it reacts with H2SO4, right, to give you hydrogen gas plus zinc SO4, right? Zinc 2 plus, SO4 is also 2 plus, so ZnSO4 it becomes, right? Does it need any balancing? The first thing in solving these questions is that you need to know whether you have to balance them or not. So let us balance this out. Is it balanced? Sulfur 1, 2 hydrogens, 2 hydrogens, zinc, 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 balanced. So first, this equation tells you that 1 mole of zinc reacts with 1 mole of sulfuric acid to give you 1 mole of hydrogen gas to form 1 mole of zinc sulfate, right? After this, see what is given to you in the question. 10 grams of hydrogen gas. So here you have 10 grams of hydrogen, right? At once calculate the moles of hydrogen at this point of time. The moles will be 10 divided by 2, it will be 5 moles, right? So this much amount of hydrogen is produced, right? H2SO4, 5 moles. You can clearly see that the relationship between them is that 1 mole zinc is equivalent to 1 mole of H2, right? So how many moles of zinc would have reacted to give this much moles of hydrogen? Well, if 1 mole of hydrogen is liberated, it is liberated from 1 mole of zinc. But if 5 moles of hydrogen is liberated, then it will be liberated from, if you multiply both sides by 5 mole of zinc, right? 5 moles of hydrogen, right? So that is how it is liberated. So now you have the moles of zinc used. So you have moles of zinc. Let me take another color. Five. Now from this, how will you get the mass of zinc? Multiplied by the molar mass. So 5 multiplied by 65. It will be 325 grams, right? That is the answer for you, right? Moving on to the weight volume relationship. Now weight volume relationship, let us understand this through an example of question. Calculate the weight of sodium bicarb to be dissociated to give 0.56 liters of carbon dioxide gas. First and foremost, write the balanced chemical equation. So how will you do that? So you have sodium bicarbonate. You should know the formula. Now when it breaks up, it forms sodium carbonate, means when you heat it, carbon dioxide, and it forms water, right? Now let us balance this out. On the very first go, you can see that there are two sodiums here. So I can put 2 here to balance this out. After that, see, there are 2 carbon atoms here. Here also 2 carbon atoms. Hydrogen check. 2 hydrogens here, 2 hydrogens here. 2, 3, the 6 oxygens here. And here also 3, 6 oxygens. The equation is balanced. Now what you have been given? You have been given 0.56 liters of carbon dioxide is formed. So this carbon dioxide formed is, one minute, it did not change color, 0.56 grams, right? Now straight away what you have to do is, you have to calculate the moles. Why am I telling you this? Because everything and anything can be calculated from moles. So first you calculate the moles. So how many moles of carbon dioxide will be here? Mass divided by molar mass, right? So whatever will be the mass of carbon dioxide, which is, okay, this is not grams, sorry, this is liters. Now the things will change. I thought that it is grams, it is liters, right? 0.56 liters. Now how do you convert from volume at STP to moles? 0.56 divided by 22.4, right? Now further, if I simplify it, let us calculate the moles there only. So you have 56 by 2240, right? So I think this will cut 56 once, and if you multiply 56 by 4, 24, 4, 5, 20, yeah. So this will be 40. So you are having 1 by 40 moles of carbon dioxide, right? If you have 1 by 40 moles of carbon dioxide, then how many moles of sodium bicarbonate will be required to produce 1 by 40 moles of carbon dioxide? That is the question that you need to answer. So how do we do that? First, from the equation you can see that 2 moles of NaHCO3 is equivalent to 1 mole of carbon dioxide, right? So similarly, so now if I write 1 by 40 moles of carbon dioxide, then how much it will be? You multiply both sides by 1 by 40, right? So this is 2 by 40, right? NaHCO3, this is carbon dioxide. So from here you can get the answer as 1 by 20 moles of NaHCO3, right? Which is nothing but 0.05 moles, right? So now you have you have the moles of sodium bicarbonate. Now simply you have to multiply it by molar mass to get the moles. Now molar mass of NaHCO3, let us get to that. I'll just do it here only. So NaHCO3 molar mass will be, sodium's mass is 23, hydrogen is 1, carbon is 12, this will be 48, right? 3 oxygens, so 1 oxygen is 16, right? It will be 48, right? So 5, 6, so this will be 14, 84, right? So 84 is the molar mass. So now you know the moles. So mass of NaHCO3 will be 84 into 0.05. This will approximately be around 420, so 4.2 grams, right? It will be around 4.2 grams. Now, the last type of relationship is the volume-volume relationship. This relationship is valid only for gases at STP, right? So let us see how does that work through this question. So here, volume of carbon monoxide gas required to react with oxygen to give 11.2 liters of carbon dioxide gas. So carbon monoxide gas reacts with oxygen to give you carbon dioxide gas. This will be half, right? Now what they have given you is, they have given you 11.2 liters of carbon dioxide. Right? Now understand that through Avogadro's law, Gay-Lussac's law of combining volumes, you know that you can, this equation means 1 volume of carbon monoxide combining with half volume of oxygen to form 1 volume of carbon dioxide. So the volumes of carbon dioxide and carbon monoxide are same. So if carbon dioxide is 11.2 liters, then carbon monoxide also will be how much? 11.2 liters, right? And that is your answer. Easy, right? Now another concept that we are going to discuss is the percentage purity of compounds. So what do I mean by percentage purity? The thing is that whenever you take out a compound from the Earth's crust, right? So if you have a compound from the Earth's crust, suppose this is the rock which contains gold, right? So there is some gold here. Now in this gold sample, you will not only have gold, you will also have certain impurities, right? Suppose this is the impurity. Now if the weight of this sample is around 100 grams, right? If the weight of the sample is 100 grams, so what do you think? Is this 100 gram the weight of the gold that is in this? No, right? This is the weight of your impurity plus gold is the weight of your sample. Now this sample I can call it is an impure sample. It's not a pure sample. Understand that, right? So what is percentage purity? It is the percentage of pure compound present in an impure sample. And how do you calculate the percentage purity? This is the pure compound, pure compound mass divided by mass of impure sample multiplied by 100 and you will get your percentage purity. Right? So this is the percentage purity, right, formula. How do we apply it to a question? Let's see that. Now, I have 80% pure limestone. So limestone is basically calcium carbonate required to produce 11 grams of carbon dioxide. Now, one thing that you have to understand and you have to know by your knowledge, that calcium carbonate, when it is heated, it breaks down into calcium oxide and carbon dioxide gas, right? So these equations, basically you should know how to write them, right? So it produces 11 grams of carbon dioxide. So the mass is given here. Now, as I tell you, if you have mass, the thing that you need to do first is to calculate the moles from that. How will you calculate moles from mass? We have already studied this in the last sections. If you people are joining us new here, please refer to the previous sessions, right, where I have discussed about the mole concept and we have also solved some questions, right? Divide this mass by molar mass of carbon dioxide, which is 44 grams. So you will get moles, right? So these many moles are of carbon dioxide, right? Now the mantra here is, when you have percentage purity thing, the mantra here is, which I did not tell you yet, only the pure compound reacts in a reaction, right? Only the pure compound reacts. So only the pure compound will give you this carbon dioxide, right? So if the pure compound only reacts and pure compound will only give you carbon dioxide, then these many moles of carbon dioxide is produced by how many moles of calcium carbonate? You can see 1 mole of carbon dioxide is produced for 1 mole of calcium carbonate. So I can directly say that here also I have 11 by 4 moles of calcium carbonate. Now, because only the pure compound reacts in the reaction, I can easily say that this is the moles of pure compound, right? And if I have the moles of pure compound, from there I can also find the mass of pure compound by multiplying these moles with molar mass. So let us multiply it. Now molar mass of calcium carbonate, calcium is 40, carbon is 12, 3 oxygens is 48. This gives you a mass of 100 grams per mole. So now you have a mass of 100 grams per mole multiplied by this, you will have 11 by 44 into 100. Right. Now this is the grams of pure calcium carbonate, right? Grams of pure calcium carbonate. What was the formula of percent purity? Pure compound mass by mass of the impure sample. What they are asking you, calculate the weight of 80% pure limestone. What is this? This is the impure sample, right? This is the impure sample, right? So this mass you have to put in the numerator and this mass you do not know. So let us get back to this equation. Pure sample is, so percentage purity is pure mass by impure mass by 100. The pure mass is 11 by 44 into 100. Percentage purity is 80%. So wait, we take this to this side, bring this to this side. Equation becomes 11 by 44 into 80 into 100 into 100. If you solve this, the value will be around 31.25 grams. So see, this is the impure sample. Okay. In this impure sample, pure compound is how much? How much is pure compound? The pure compound is around 11 by 44 into 100 grams, right? And this is the percentage purity. So like this, you can solve these kind of equations and these kind of questions as well. Now, the next concept is of limiting reagent. Limiting reagent. So how do you understand this concept of limiting reagent? Well, quite simply, what you do is, suppose I have one red colored pen, right? I have a red colored crayon, suppose, right? And this red colored crayon, I have to put on a piece of paper, right? I have to color this piece of paper red. Now, so red crayon with a white paper will give me what? Will give me a red colored one paper, right? Now suppose I increase the number of paper to, suppose, 30 papers, right? But the number of crayons is just 2. What do you think, how many? And one more thing, one crayon is completely required to color one full sheet of paper, right? So if I have 2 crayons and 30 sheets of plain paper, how many colored papers I can get? Well, that is the question that I want to ask. How many colored papers I can get? Simply, it is the crayon which decides how many colored papers you will get. You will basically get here just 2 colored papers because the crayon number is 2. This crayon is called the limiting reagent, or we call it LR, right? Because it limits the amount of product that you can get. Now, how do you find this limiting reagent? Well, that is a question that I'm going to answer in the next slide. So you have 48 grams of carbon. The first thing that you have to do is calculate the moles of each species that is given to you. Now, carbon's molar mass is 12. Oxygen's molar mass is, this is O2. O2 means 32, right? So if you have 12 here, what it will be? 4 moles. Here it will be 1 mole. And here obviously it is, we don't know. Now, understand this, do not fall into the trap of trying to calculate it directly. Now, from now on, because I've told you the concept of limiting reagent, you always have to find the limiting reagent, and the moles of that limiting reagent will decide how many moles of product you will get. That is the mantra that you need to follow, right? So now let's get started to that. 4 moles and 1 mole. Still, how to find the limiting reagent? Simply, the first, after you find the moles, balance the equation. Now, is the equation balanced? This equation is balanced, so no problem here. 1 carbon, 1 oxygen, giving 1 CO2. Now, the stoichiometric, divide the moles by the stoichiometric coefficients of the particular species. So this stoichiometric coefficient is 1, so divided by 1. This is also 1 divided by 1. So this here I'll get 4 here, here I'll get 1. The lower this number is, for whatever species this number is lowest, that is the limiting reagent. This is lower, so this is your LR, right? This is your limiting reagent. Now this limiting reagent now will decide how much amount of carbon dioxide is formed. This is called the excess reagent. Sometimes they will tell you that this reagent is in excess. If one reagent is in excess, the other one is not, means the other one is the limiting reagent. This is the excess reagent, this is the limiting reagent. Now, how does it help me to find how many moles of carbon dioxide is formed? Well, quite simply, here you have, if you have carbon, oxygen, let me just write it down again, what is the issue in that, right? So you have 4 moles earlier of this, 1 mole of this decides this, right? So this will come, limiting reagent reacts completely in the reaction. So you can write this down, limiting reagent is the reagent which reacts completely in the reaction and will become 0 at the end of the reaction. So in the start of the reaction you have this, at the end of reaction this will become 0, and because 1 mole of this reacts with 1 mole of this, 1 mole from these 4 moles of carbon will react. So you are left with 3 moles of carbon. Now 1 mole of oxygen gives you 1 mole of carbon dioxide. So here you will have 1 mole of carbon dioxide. So that is essentially the concept of limiting reagent for you. Let us do this question. Right. Calculate the amount of sodium oxide formed when 2.3 grams of sodium reacts with 32 grams of oxygen. So how do we do that? First, write the balanced chemical equation. Let us do that, and only through that you can get it. So you have sodium reacting with oxygen to form Na2O, right? So balance it, 2 nitrogens are there here, so I can put 2 here, and 1 oxygen, so I can put half here, right? So they have given 2.3 grams of sodium. So let me take another color. So 2.3 grams of sodium, 3.2 grams of oxygen, right? Calculate the moles first. Sodium's molar mass is 23. So 2.3 divided by 23 gives you 0.1 moles here, and oxygen's is also 32 grams mole, so 0.1 mole here. Now if you divide each of these moles, right, with the stoichiometric coefficient, this will be 0.1 by 2, this will be 0.1 multiplied by 2, right? You're dividing, so 1 by 2 division, it goes up, so this will be 0.2 and this will be 0.05. So this you can clearly see as a lower value, so this is your LR. What is your LR? This is your limiting reagent. Now after you have found out the limiting reagent, then nothing has to be done. Moles you have already calculated, right? So now here you can clearly see that 2 moles of sodium are equivalent to 1 mole of Na2O, right? So divide both sides by 2, make 1 mole here, right? This is clear. So now if I have 0.1 moles of sodium, multiply both sides by 0.1, moles of Na2O, right? So from here you will get 0.05 moles of Na2O, right? Next, to find the amount, only they asked. Amount of a substance means moles, right? Amount basically means moles. So here also they are asking about right? So they are asking about moles. So this is the moles of Na2O formula, right? With this, I end this session, right? And you will be moving forward in the next session with mathematics. But before that, as I tell you every time, please scan this Google QR code, fill this form so that we can get to know you better, and we will send you constant notifications. Now to join us, join our family at Sri Chaitanya Academy, scan this Telegram QR code. This Telegram QR code will keep you updated with all the things which are happening at Sri Chaitanya Academy. So I take leave now, and next you can meet maths ma'am, right? So bye from my side.